it with one problem, all or nothing? Would you ace it? On the graph, could you have been able to tell exactly what it was? Just from the graph? No. But here's my question. Looking at the graph, trying to take the limit as x approaches 2 from below and from above, does the limit exist? Okay, let's vote. I think half of you would fail the quiz and half of you would pass. If you think the limit does not exist, raise your hand. If you think the limit does exist, raise your hand. Some of you didn't vote. Okay. We're almost half-half. A few more have voted for the does exist option. The limit.
There is no diner. Is the limit 12? I want to hear the answer.
But pause. I'm not asking whether or not the diner is open. I'm asking, does the limit exist? What word do you need for limits? Approach. Are they approaching the same spot? Are they going to the same diner? Yes. It might be locked, but they're going to the same place. So, one more time. Does, just answer out loud, the limit exist? Yes. Because when you answer the limit problem, you are not talking about the diner, you are talking about the approach. Are we tracking? So, the limit does exist. The whole does not negate that. Technically, what you're thinking is, but the function is not continuous. That's thinking. There's a whole calculus definition for every card that goes with it, but the function is not continuous. You're right, there's a problem there. But the limit, the approach, does exist because the two cars are headed to the same place. So first of all, the limit does exist, yes. And second of all, what does it equal? 11, 12, 11.5. The graph was not perfect. So you had to maybe dig a little deeper to say exactly what the limit was. Who found it and what was it? It was 12. How'd you find it? Okay, you could plug it into your calculator, and if you plugged it into your calculator, you would have looked, okay, remember, the goal is not to be able to use our calculator for these problems. That is not the goal at all. But it's to get an idea of the approach. If you were coming, wait, what's this mean again? From below. Why am I making it red? Because the red's from below. You could think of it as the red diner guy, right? Okay. As you went from below, if you were using your calculator, what kind of numbers should you have been plugging in? 1.9, 1.99, 1.999, 1.999, looking at the y's and saying, are they getting closer to something? And what did you see them getting closer to? Good. However, you also had to look from above. Now, we have the picture. So some of you could have looked at the picture and been like, oh, it's going to the same spot. One's 12, the other's 12. Done. But maybe not all of you realize you could have done that. So if you had plugged in from the other side, what kinds of numbers would have been on the other side of 2? Yeah, 2.1, 2.01, 2.001. Good. Looking at the y's, what were the y's approaching? Do they agree? So the limit exists. Now, who figured out a way to find 12 without the graph and without the calculator? Joe. Give me 1 second. Let me rewrite. But yes, you're right. Limit as x approaches 2 of 3x squared minus 12. Good. Now go, Joe. Now careful. This does not equal that and does not equal that because this is a limit and that is a function. So careful. You would need to keep rewriting limit. It's as though you were writing something like square root of 5 squared plus 1. And all of a sudden you're like, oh, that's 5 squared plus 1. Oh, that's 26. Wrong. You can't just randomly stop writing, right? You can't just stop writing the square root. So what can't you stop writing if you're simplifying things? You can't stop writing the limit. Okay, that's just a quick little notation-y thing. You can't stop writing the limit until you take it. Let me show you another explanation real quick. What if it was to be okay, what if it was this one? When do you stop writing the limit? Or sorry, when do you stop writing the square root? When you do it, right? So when do you stop writing the limit? When you solve it. Does that make sense? When you find it. Then you can stop writing the limit, but not before. Okay, coming back. It's a good illustration. I should use that again. Okay, so, Joe, what do I do now that I have it all nice and factored and pretty? What disappeared? The limit. Why did it disappear? Because we found it. Good job. That is the mathematical way of finding 12. Basically what it's doing is considering this function, realizing that 2 is a whole. And so what if I remove the whole, ignore the whole, and plug in what should have been there if the whole had not have been? Would not have been. This is a little bit off, isn't it? Hold on. Now we're having too much fun. This begs the question, when does the limit not exist? The limit exists as long as the two approaches agree. Don't care whether the diner is locked or open, burned down or there. The limit exists as long as the two approaches agree. So that kind of begs the question, when does the limit not exist? The limit does not exist if the two approaches do not agree. And here are 1, 2, 3, 4 different illustrations of when the approaches will not agree. I'll give you a second to get them down. I'm going to zoom in. You guys can catch up on the last ones if you need to once I zoom in. But the first way that the limit will not exist is if the limit as x approaches a from below equals L1, and the limit from above is L2, and these do not agree. If where the limit from below is approaching does not agree with where the limit from above is approaching, the limit does not exist. Now, can anyone think of a scenario? Can anyone think of a scenario? With my diner example, the two guys trying to meet for breakfast, that could go along with this picture, this graph. There is one. I can think of one, but can you? Colby.
Different stores, but the same franchise.
Okay, that's one good way of thinking about it. Except different stores of the same franchise, it might be a little awkward to explain why that one is closed and the other one is open. But we know that Starbucks has like different closing times depending on which one. Most of them open at the same time. So.
Chinese McDonald's and an American McDonald's. There you go.
There you go. So this one is approaching in a totally different time zone and it's open, and this one's approaching in a totally different time zone and it's the wrong time of day. Okay, that's interesting. I had never thought of that before. Okay. So maybe both of them are going to McDonald's, but one of them is in a different country, and so the time is not right. Hopefully, two people trying to meet would know if they're in different countries. It's not going to work out if they go to their local McDonald's. But anyway, maybe something that would make sense a little bit more. But good ideas. Two people in the same town going to a different Starbucks, that's possible, right? Huh? Maybe, but that would be at two totally different locations. Does that make sense?
Or one goes from one road and the other goes from the opposite road.
Yeah, but then they're still going to a certain location. They're not going to the same place. Huh? Yeah, but then it'd be matching up. You know what I mean? Yeah, they can't be going to the same location. So what's an explanation as to how two guys are trying to meet for breakfast?
They get lost. One dies. One of them gets in a car accident. One of them. Thank you.
Okay. Very creative. Let's see if mine makes sense. Can I just give you mine and see if it makes sense? If it doesn't, that's okay. We'll go back to the time zone one. Or the two different locations, which is pretty good, just maybe they have different hours. Okay. Here's my idea. My idea is there's not multiple of the same. There's just one. Let's say it's like a little mom and pop joint, right? But let's say one looks up online address and the other one looks up on like Yelp. Which one's possibly updated more frequently? Their online website or their Yelp? No idea? Interesting. Let's say one looks up Yelp. Which one's going to be updated more? Yelp, right? That are reviewing, not automatically, but frequently reviewing, like, oh, 1 day ago, 2 days ago, etc. The Yelp one's like, hey, new location. The other one burned down. Oh, one guy goes to the right place, is sitting down waiting for breakfast. The other guy went to the old location. He wasn't able to get in. Anyway, it's a way of thinking about it. And the Chinese McDonald's in the two different time zones because it makes sense that they would be meeting. All right, anyway, you're right. They definitely won't meet. Okay, so two guys headed at one time, right, to two very different locations. That guy's not getting in. That guy's sitting down waiting, being like, hey, dude, where are you? Anyway, he's having his coffee, so he's good. Speaking of coffee, speaking of breakfast, pancake breakfast, Saturday morning, come support missions, pancakes, and you can go look for hidden treasures in the rummage sale. Anytime between 7 and 10:30. It's breakfast. P.S. It's kind of all you can eat and there will be bacon. All right, so here we go. You have someone in your class that would love to sell you tickets. Anyway, coming back. Or you can just show up. The limit will not exist if, coming from two different directions, two different heights are being approached. If the one-sided limits do not agree, the limit does not exist. The limit will not exist if the one-sided limits do not agree. We'll keep chanting that as we go on. But pause. When else will the limit not exist? Technically, the limit, if you read the informal definition, only exists if the y values are approaching a single constant. In this first one, are the one-sided limits agreeing? Are they headed the same height? Yeah. They are agreeing. That is true. So actually, we are going to put an answer to this one where we would not put an answer to this one. We'll talk about in a second. But technically, I'm going to put this answer in quotation marks. Well, I shouldn't do that. I'm going to put the DNE in quotation marks. The limit being a single constant does not exist. A single constant limiting value of this function does not exist. But the one-sided limits agree. So the answer would be where they are approaching. The one-sided limits agree, so therefore the answer to the limit would be positive infinity, would be where they are in agreement headed. I used to have napkins. They went missing. I can put it on my desk. So, guys, why did I write the infinity? Because they agree. And that's where they're approaching. Good. Yeah, that's where they're approaching. The two-sided limits, the two guys in the diner, they'll be driving for quite a while. But they're both headed the same place, right? Could I make an argument for a single limiting constant value not existing? Yes, I could. But are we going to answer DNE with this? No. Why? Because they agree. Am I going to put a number? No. What am I going to put? Positive infinity. What if they agreed going down? Negative infinity. What if they disagree? There's one and only one answer, and the one and only one answer is?
Absolute.
But, John, it was a good idea. Let me come back here real quick. He said plus or minus infinity. What was he doing? He was looking at just from below, and then he was looking at just from above. So I could go ahead and I could answer for the just from below and just from above. I could answer the limit as x approaches a from below is negative infinity. And I could answer the limit as x approaches a from above is positive infinity. But what do I have to say in between those two? So what's the limit? DNE. Why? The one-sided limits do not agree. Colby.
If you say absolute value.
Well, that would be changing the function. But if the limit was of the absolute value, you're right, the limit would be positive infinity. But since the question, I didn't put an absolute value, we can't change it to make it what we want it to be. Ooh, life lesson to that. Think about it. Anyway. Sometimes you just got to take things as they are and not try to change them to make them what you want them to be. Letter C. Can you guys graph this guy? Can you graph this guy on your calculator? He's quite an interesting one. It's more interesting than probably you even think he is. And I want you guys to look around A and zoom in, zoom in, zoom in, zoom in, zoom in, zoom in. Because I don't know about you guys. Maybe he's approaching 0 if I zoom in enough. And if I zoom in enough. And if I zoom in enough. Right down here. Sine of 1 over x. The limit as x approaches 0. You can try to plug in 0, because some of you are like, maybe that plugging in thing is a shortcut. Maybe I'll like that. And even you're like, well, but sometimes you plug in and get 0 over 0, but then Joe did that cool factoring thing, and then we plugged in. Try plugging in 0, but what does the calculator show if you do second trace value? What happens if you plug in 0? Error does not exist. 1 over 0. Struggle. Check it out in the calculator. Have Colby show you what's happening when he zooms in, zooms in, zooms in, zooms in. I wish you could pinch and zoom, but as you keep on zooming, what keeps on happening? It freaks out.
This is kind of weird.
It is kind of weird, I agree. Keep on zooming in, though.
Okay.
Zoom in. There's something weird going on in there. Now, I gave guys a very rough sketch. I did not give a pretty gorgeous, accurate sketch. I just gave you an idea of what's going on.
This is kind of weird.
Looks like a barcode. Keep zooming in.
Still?
Because it looks kind of like maybe it's going to hit 0 at 0. I mean, I know that it says it doesn't in, but maybe towards the origin. Is anybody else's graph freaking out like a barcode?
Yes.
No? Uh-oh. Let me see yours, Dean. Why is it not freaking out? It's supposed to freak out. Yeah, see, that's what... Oh, oh yours is paused. Oh, yours is sad.
Okay. I think I did.
Let's try rating. There you go. Now zoom in. You were just in degrees, so it was kind of freaking out a little bit. Oh, yeah, it doesn't look bad, right? Like it should be okay. But now, check out what's really going on. See, it still looks like maybe, but if you keep zoom in, zoom in, zoom in. Janelle, hold yours up. Hold yours up real quick, the graph. Keeps on freaking out. Right? Now we see it freaking out? Oh, you can't zoom in. That's a bummer.
I'm in degrees. Should I go?
Yeah, go right here.
Yeah, this is for the 5 gallons of milk.
There you go. That better?
You mean milk? Chocolate milk is more accepted on society.
Looks like it was freaking out.
This is for like 5 gallons of milk.
All right. Somebody who has a really good freaking out graph. Let me see it real quick, just for those who don't have a graph. Oh, yeah, that's good. That's good.
Is that good?
This one zoomed in. This one zoomed in to, let's see, 0.009, left, right, up, down. 0.009. Is it going to a nice little point in the middle? Nope. And as you keep on zooming in, guess what's going to keep on happening? It's going to keep freaking out, freaking out. Yeah, now you got it. Freaking out. Okay? Here's the dealio. We're going to talk about some algebraic ways of dealing with it, mostly in section 12.2, just a little bit in section 12.1 to finish off this section right now. But I want you guys to think about, just a second ago I said, maybe this plugging in idea is kind of cool sometimes. And maybe it works sometimes. And that one that we just saw with the hole, okay, it was a bit of a struggle because you couldn't plug in as is because you would get 0 over 0. But then Joe was like, well, we can play with it, and we can maybe get it to where we can plug in. And that was the answer. That's what the calculator said. That's what the graph, if it was perfect, would have said. But this one, if we go to plug in 0, if we go to plug in 0, isn't it sine of 1 over 0? 0 over 0 is a whole. Maybe I can deal with that because a whole, a limit can still exist. But 1 over 0, does anyone remember where we've seen 1 over 0 or 2 over 0 or 4 over 0 before? We have seen it with tangent. And with tangent, when you had 1 over 0, tangent would be undefined. And do you remember what was at that undefined spot? 90. Vertical asymptote, which indicated that the function was going to infinity or negative infinity. 0 over 0 is a whole, it's a set finite space, point space that's missing. That's awkward, but that's missing, but it's a point in space. Number over 0 is what we call infinite form. And that is indicating some sort of infinite quantity. And if we took sine of infinity or sine of negative infinity, which we can't do and plug into our calculator, but we can think about. If we take sine of higher and higher and higher and higher and higher and higher and higher values, is sine getting closer and closer and closer to anything? What's sine doing forever? Waving. Is it getting closer to anything? It's just oscillating. Just waving over and over and over, between 1 and -1, between 1 and -1, between 1 and -1, between 1 and -1, never making up its mind, never converging, never getting closer and closer and closer and closer to one limiting value. Therefore, what is going to not exist? The limit. Those of you that were pondering algebraic ways of doing it, that would be an algebraic way of considering why this does not exist without a calculator and without a table. Okay. I've been mentioning that this is just the beginning. We are going to have a little bit of fun with limits at the very end of 12.1, like super easy ones. But before we get to the super easy ones, I know it's like chapel schedule, but then it's like not, but then it's, anyway. Hang in there. The bell will ring when it rings.
Isn't it pep rally schedule today?
Yes, sorry. It's like chapel schedule. It's pep rally schedule. Different. We're obviously not in chapel. As we go and as we plug in, wait, hold on, not plugging in. Graphically, how do we consider this graph if it's a piecewise function?
I don't know.
Substitution might be helpful at one point, but think bigger. No, think bigger. This is the limit that we're going to be considering. That's true. But I want you guys to consider the graph of this function. I'm asking, can you figure out what the graph is? So don't go straight to trying to answer this. We'll talk about this in a second. I'm curious, can you get me a graph? How? Piece by piece. So pick one. Pick a piece. How about the top one? If I just had the top guy, wouldn't that be y equals mx plus b? What would be my intercept, my b? Plus 0. Oh, so it's going to hit at 0. What x value should I be plugging in? I don't know. Maybe 2, maybe 1, maybe 0. Anything less than 2? So if I plug in 1, I could just plug in points if I wanted to. I would have -2, which, slope is down 2 over 1. If I plug in 2, that'd be down 4 over 1. Why do I have a filled in point at 2? Good. Or equal to. I got it. Or equal to. Okay, so I filled in the circle. 2 and 1 and 0 and all the points, all those, x less than or equal to 2, all those x values. That's the graph. But how about the other piece? Could I plug in 3? Suppose. 9 minus 12 would be -3. -3 plus 1 is -2. Is that right?
Yes.
9 minus 12, -3, -2 plus 1. Okay, so that'd be 2. -2. 9 minus 12, -3, -3 plus 1, -2.
Should we do 2 though?
Oh, thank you. That'd be up. Thank you. I was putting it at 4 for some silly reason. Okay, if I plug in 4, 16 minus 16 is 0. 0 plus 1 is 1. Okay. This isn't supposed to really start at 3, though. Where is this supposed to start? 2.1. So where would it be at 2? And I'll put a hole there, and then I'll just connect from there on out. So where would it be at 2? 4 minus 8 is -4. -4 plus 1 is -3. Oh. You see him? He's an upwards parabola. Cannot be at 2 because there is not an or equal to on the inequality of 2. So I only fill in where I have the or equal, which is why this side has the or equal and that side doesn't. Kiddos, if I wanted you to take the limit as x approaches 2 of this piecewise function, wouldn't you have to come on 2 different pieces to come towards the 2? And remember, we don't care about all the extra stuff. We care real close. But even real close, 2.1 is on the parabola. 1.9 is on the line. And as we look at it, what would be your answer for the limit?
Does not exist.
Good. Because they're not approaching the same location. Could I answer for the limit as x approaches below 2? Yeah, I could. Can you guys tell what's happening as I come from below 2, which would be technically the negative 2x portion? Where am I headed?
Down.
Negative 1, 2, 3, 4, right? Joe, does it work with our trick? Plugging in? Does it?
Oh, yeah.
Yeah. If I come from the other direction, which would be of the other piece, what should that one approach? Negative 3. Does it work with our trick of plugging in? 4 minus 12 plus 1, negative 3. Huh?
You put it at negative 2.
No, I did 2 That is negative 4. Oh, did I do my tick marks? Tick marks wrong? I did. Thank you, Colby. My tick marks, I didn't draw this one nicely, so I didn't realize that was my negative 4. So then this would be my negative 3, and that would be my negative 2. Thanks. All better. But kiddos, this is a rough example. This is an example we're going to work on more and more and more as we play with the algebraic way of solving. Once again, the goal is not to have a graph every time, but it is to be able to look at a graph and realize, oh, the limit does not exist. Those two one-sided limits do not agree. But yet to also look at another graph and say the limit does exist because the one-sided limits do agree. But let's end today's class with something, oh, that'd be way too much fun. We'll pause on that. Let's end with something a little bit easier. And you might be like, this does not look easier. I know it doesn't, but in a way, it's going to be. And that's going to be even better. So, let me give you guys a couple seconds. Let me actually give you both pages. The properties you're not going to have to memorize. This is basically the end of notes. The properties you're not going to have to memorize. Let me turn off both lights so you can see it better. But the properties are going to let us simplify. Some of these problems. Oh, my letters got all weird. That's why it looks funny. Don't worry. The B is supposed to be way over here somewhere. I don't know why it got all off. Yeah. Oh, properties are too small. It was worth a try. I'll zoom in. It was worth a try. Is that better? These properties help us if they give us something like no graph, no function, but they give us clues. And they're like, hey, I'm not going to tell you much, but I am going to tell you a limit of this guy and a limit of that guy. They're giving us two separate little clues. And then they say, can you use the properties to tell us what the limits will be? And the cool thing is, according to these properties, we can do things like bring this negative 2, the multiplication, out. And when we bring the negative 2 out, we can say, oh, hey, do we know the limit of g? And the answer is yes. So we can find this limit just by throwing in the 6 and being like, oh, hey, this is just negative 12. Taking the clue and taking a scalar multiple property up above and saying, sweet, negative 2 times 6, negative 12. You could also think taking an, that's not going to help. Never mind. It's not going to help. As you guys are writing, you should have gotten to the sum or difference one yet. What do you think I'm going to be able to do for letter B then? If it says the limit as x goes to c of f plus g. Just add them. 3 plus 6 is... If it was a minus, I would have subtracted them. Psh, I like these problems. Letter C, if you've gotten to the quotient property yet. What do you think we're going to do?
Just 3 over 6.
Just divide them. And if you've gotten to the power property yet, power property, but, couldn't this be rewritten as f of x to the 1/2, which is a power? What can I do to powers? Raise the limit to that power. So what can I do with this guy? Square root the, who's f? 3. So maybe it takes some time to write the properties, but maybe the problems are actually really simple. Now some of you might need a little more time to write down this page, but I want to show you the last topic, which is why homework is still due tomorrow. So the last one says, for really nice, well-behaved functions, aka no 0 over zeros, no number over zeros, no piecewise functions, limits can be as easy as plugging in. Limits can be as easy as plugging in. For really nice, well-behaved, no holes, no vertical asymptotes, no jumps, no piecewise functions, no you'll come to learn absolute values. Limits can be as easy as plugging in. What do I mean? What's the limit as x goes to 4 of x squared? Calculators, graphs, no, plug in. 4 squared is 16. Dun, 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 dun. Limit as x goes to 4 of 5x. Oh, we need a calculator, we need a graph, we need a... No, plug in. 5 times 4 is just... What's limit?
Oh, wait, 3.
What's limit? Could some of them require a little bit of previous work on, say, something called the unit?
Sheet or chart?
I give up. Yeah, but all you gotta do is plug in. Bye, guys. See you later. Use your calculator. Use your graphs. But enjoy the plugging in. Bye. End of the day, they should be done. I'm on the back page of the second half.